Hi everyone. I'm really sorry I can't be in the lesson with you today. I think I mentioned before Easter holidays that I was doing this thing called jury service, or I have been during the holidays, which is where you get randomly selected by the government to go to court to sit on a jury to help make a decision about whether someone's guilty or not guilty in a court case. So I'm hoping it's just going to be today's lesson that I missed this week. But anyway, I'm sorry I can't be there, and that's why. But I didn't want us to get behind on the work we need to do this week, so I've made you a little video to introduce our next chapter, which is binomial expansion. So if you want to find this in the textbook, it's in the Pure 1 textbook, and it's chapter 8, binomial expansion, and we're just going to look at the first section of the chapter today. Which is all about Pascal's triangle, something called Pascal's triangle. Now, Pascal is the name of a mathematician. I guess this triangle is named after him, actually. If we look on this page that I prepared here for us, I've got the name of who this triangle should be named after. So we should really call it, oh my goodness, Zhu-Shiji's triangle. I'm really sorry if I butchered the pronunciation of that name. Since Zhu, who was a Chinese mathematician from the 14th century, discovered it 300 years before Pascal, so whoever you want to name it after, it's basically a list of numbers that form loads of different lovely patterns, which I've set as a task for the end of the lesson if you finish everything else to sort of investigate some of these patterns. But basically you start drawing this triangle with a 1, a 1 and a 1. And then you add the numbers above together to get the next number. So 1 plus 1 is 2, and then on the outside of the triangle we always just have 1s. And the next row is formed by starting and ending with a 1, but then you add the two numbers above to find the number beneath. So 1 plus 2 is 3, and 1 plus 2 is 3, so we get 1, 3, 3, 1, and so on. And it just so happens that this pattern, I mean, there are loads of applications for it, but it has a lot of applications in something we called combinatorics, which is a branch of maths that is used a lot in probability and finding probabilities, because it's all about looking at combinations of doing things. And when we look at binomial expansion, it might seem like this is nothing to do with combinations of things. But say I'm expanding some brackets, a plus b cubed. Let's start with an easy example. We'll start off, if I were to just write out these brackets, I mean, I'm going to start off with a cubed, so a times a times a is a cubed. And there's only one way of forming an a cubed if I expand these brackets. But I'm also going to have a squared times b in there. Like, I'm not sure how many yet, but I'm going to have some terms with a squared b. And the ways of getting an a squared b in this expansion of these brackets is by multiplying a and b together. Or I could do a and b and then a. Or I could do b, then a, then a. So there are 3 different ways that I can form the term a squared b. So there's going to be 3 of them in my expansion. Similarly, if I look at the next term, so I'll also have some number of ab squareds, and I'll do this in green. So to make an ab squared, I can have a times b times b. That's one way of doing it from these 3 brackets. Another way would be b a times b. And then finally I could have, I'm going to have to start with b times a. So there's also 3 ways of getting ab squared. So there's going to be 3 of them in my expansion. And finally, just like there was only one way of getting a cubed, which is a times a times a, I can do b times b times b. So that's b cubed, but there's only one way of doing that. I just need b times b times b. There's not, like, there's different combinations of ways I can make that term. So it's just going to be one lot of b cubed. So that's why combinations of ways of doing things feeds into this topic. And this is why the coefficients, or the numbers in Pascal's triangle, give us the coefficients of our binomial expansion. So if you remember that Pascal's triangle I just showed you, it started off 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. You'll notice here that my coefficients are 1, 3, 3, 1, which is the fourth row of Pascal's triangle. So I'll go over this again with some more structured examples. I basically just told you in the start of the chapter. But to find the coefficients of your terms in your binomial expansion, so why it's called a binomial expansion, bi usually means 2 and nomial means terms. So in this chapter we're really looking at a bracket with 2 things in it that we're raising to a power. So why this works, or how this works, is I can read them off of Pascal's triangle. If I can just quickly sketch out Pascal's triangle and remember how it's formed really quickly. It's quite a simple pattern to follow. You can generate quite a few rows of it quite quickly. I can look at the power that I'm raising to. In my example here it was 3, and I add 1 to it and I go to that row of Pascal's triangle, and then I can just fill in what the coefficients are of each term. And I still need to work out, okay, I've got a cubed, I've got a squared b, I've got ab squared, and I've got b cubed, and then get them in the right order. But then I could just write in what those coefficients are from reading it from Pascal's triangle. Okay, so let's try and look at this a bit more slowly now with a few more examples. So looking for patterns in expanding binomials. So here, if we were having a lesson, I'd probably get you to expand some of these brackets yourselves, just by hand, kind of the slow way, the old-fashioned way, like we've been doing. But you'll notice that if I expand, a plus b raised to the power of 0, I just get 1. If I expand it to the power of 1, I just get a plus b. I've written the 1s in there because the 1s are in Pascal's triangle, so it's really just to show you the pattern. So this is what I'm getting. Another thing just to highlight that's kind of helpful to remember, I'm sure we'll see it again, is that whatever your power is on your brackets, your powers of each term should always add up to that. So 2 obviously adds up to 2, then I've got a to the power of 1 and b to the power of 1 here, so 1 plus 1 is also 2, so that works. And then I've got b squared here, so that's also 2. So you can always check that you've got the right terms by just checking that. Just to give you another example, if my brackets are being cubed, all my powers of each of my individual terms need to add to 3. So obviously a cubed, the power is 3. A squared and b to the power of 1, well 2 plus 1 is equal to 3, and for the third term, a is to the power of 1 and b to the power of 2. 1 plus 2 is also 3, so that one's good, and b cubed is obviously 3. So it's just another pattern that's quite useful to remember. What do you notice about the coefficients? So they follow Pascal's triangle, which we're going to explore on the next slide. And the powers of a and b, so we also said actually that the powers add in each term the power on the bracket on the original brackets. But we also have an additional pattern here, that's the power of a decreases each time, starting at the highest power from the bracket. So here we start with a to the power of 3, and then that decreases by 1 each time. So we've got a squared, a to the power of 1. Technically in this last term we have a to the power of 0, which is just 1. So the power of a is decreasing by 1 each time, and the power of b is increasing by 1 each time. So technically in this first term here, I've got b to the power of 0. That's just 1. In the second term, I've got b to the power of 1, so the power is increased by 1. Then I've got b squared, power's increased by 1 in the third term, and power increases by 1 again in the last term. So And by spotting these patterns, it just helps you do the expansion much more quickly and write out what each of the different terms will be. So I hope that makes sense. Okay, Pascal's triangle then. There's a little typo here that I noticed, so I'll just correct that. This should be a 5, of course, because 4 plus 1 adds to make 5. Right, so I've kind of introduced to you how we draw Pascal's triangle, where the numbers come from. What do these notes say? So the second number of each row tells us what row we should use for an expansion. Okay, so yeah, so if we look at the second number in each row, instead of remembering, take the power in the bracket and add 1 and go to that row. So say I had a plus b squared. The way I explained it before previously was add 1 to 2 and look for the third row, 1, 2, third row. These are my coefficients for expanding that bracket. We could alternatively just look at the second number in each row, and that would tell me, so for the power, if the second number in that row is 2, that's for a power of 2 on my brackets. Those are my coefficients. If the second number is 3, that's for expanding, for example, a plus b to the power of 3, and so on. So that's another way of remembering it. If we were expanding 2 plus x to the power of 4, the power is 4, so we use this row because 4 is the second number in that row. Or you could remember it as that's the fifth row. So add 1 to 4 and find that row. Yeah, it's useful to memorise stuff at A-level maths. There's no denying that, to be honest. So if you can memorise these numbers, that will be really useful to you. Help speed things up. Okay, we'll see later why each row gives us the coefficients in the expansion. I've kind of given you a bit of an explanation already about why that works. But we'll try and explain it again as well, because it's a little bit complicated. Right, so find the expansion of 2 plus 3x to the power of 4. Now, how would this Pascal's thing help me speed that along? Well, I've got a power of 4. So if I go back to Pascal's triangle, my coefficients are going to be in this row. They're going to be 1, 4, 6, 4, 1. I know that because it's the 5th row of Pascal's triangle. You can remember it that way because I take the power and add 1 and find that row, 5th. Or I can look and see what is the second number in the row. I'm looking for a number 4 because that's the power of my brackets. So either way you want to remember it, it's going to be this row. So the coefficients are going to be 1, 4, 6, 4, 1, 4, 6, 4, 1. And then I want the powers of 2 to go down by 1 each time, so in descending order. So I want to start with the highest power of 2, and that's going to be, the highest power is going to be to the power of 4, because that's the power of my brackets. I'm going to start with 2 to the power of 4, and then just write out the powers descending by 1 each time. And then I want to write the 3x part in increasing powers. So I'm going to start with the power of 0 and increase by 1 each time until I get to 3x to the power of 4. So I'm going to have 3x to the power of 0. It's really important to write in your brackets here to show that you're raising the whole of the term 3x to the power. It can be a common mistake to just think that the squared part, for example here, just applies to the 2 if you don't draw the brackets in. But obviously 3x all squared is 9x squared, not 3x squared. So we've got 3x cubed and 3x to the power of 4. Okay, now if you write it out nicely like this, the next bit's going to become really easy. Oh, sorry. Right. So my actual expansion is just going to be the coefficient times the 2 to the power term times the 3x to the power term. So my first term in my expansion is going to be 1 times 2 to the power of 4 times 3x to the power of 0. So let me just write out my brackets here. So this was 2 plus 3x all to the power of 4, and that's going to be equal to this. Okay, my second term is going to be the next column over here. It's going to be 4, the coefficient, times 2 cubed times 3x to the power of 1. I'll write it out just for completeness, but obviously we could skip a few steps here. The third term is going to be 6 times 2 squared times 3x all squared plus 4. The next one is going to be this column over here, times 2 to the power of 1 times 3x cubed. And then finally I'm going to have 1 times 2 to the power of 0 times 3x4. Now of course once you get used to this you don't have to write it all out. For example, here I've got a 1 and a 1, 3x to the power of 0 is just 1. So I would just write out what 2 to the power of 4 is. 2 to the power of 4 is 16. Then I've got 4 times 8 times 3x. So 32 times 3 is 96. Is it 96x? And then I've got, gosh, this is testing my mental arithmetic. I should have got a calculator ready. Feel free to fast forward this bit if you're find this a bit tedious. So 6 times 4 is 24, times by 9. Oh gosh, 24 times 9. Hang on, I am going to get a calculator here, bear with me. Okay, so that one's 216 lots of x squared. And then the next term's going to be 4 times 2 times 27, which is 3 cubed. So that one is also 216, but x cubed this time, because this term expanded will give me 27x cubed. And then last term I'm going to have 1 times 1 times 3x to the power of 4. So 27 times 3 is 81. So I'm going to have 81 lots of x to the power of 4. So I got the 81 from 3 to the power of 4. And that is my expansion, and I hope you'll agree that is a lot quicker than having to expand the brackets manually, especially once you get the hang of it. Okay, let's see if I can do this example over here really quickly. So here we've got a bracket, 2 terms in a bracket to the power of 3. So I'm going to be looking at the 4th row of Pascal's triangle. In other words, 1, 2, 1, 1, 3, 3, 1. In other words, this row. So my coefficients are going to be 1, 3, 3, 1, and I'm going to write 3 in descending powers. So 3 cubed, 3 squared, 3 to the power of 1, and 3 to the power of 0. And I'll just write out what they are. 9, 3 and 1, and then I'm going to do minus 2, so the sign matters in the brackets. If I have a minus 2x, that's what I need to raise to the power each time. If it's plus, I use plus. So this is really important. So minus 2x to the power of 0, so remember the powers are increasing. Then minus 2x to the power of 1, minus 2x to the power of 2, and minus 2x to the power of 3, and then I can just write out what this will be. So that will be 1, that will be minus 2x, that will be 4x squared, and this one will be, remember, minus 8x cubed. That's because I've got minus 2x times itself 3 times, so it's going to give me a negative answer. So watch out for the signs. That's a common thing that students seem to get wrong. Okay, so the expansion of 3 minus 2x to the power of 3 is going to be, well, this first term is going to give me 1 times 1 times 27. It's going to be 27. The second term is going to give me 3 times 9 times minus 2x. So I'll do this in a few steps. So I'm going to have 3 times 9 is 27 plus 27 times minus 2x. The next term is going to be 3 times 3, which is 9, times 4x squared. The last term is going to be 1 times 1 times minus 8x cubed, so I can just write minus 8x cubed on there, and then I'll just simplify those brackets that I kind of left. So 27 times minus 2 is minus 54. X, 9 times 4 is 36, that's going to be 36x squared minus 8x cubed, and that is my second expansion. Hope you're getting the hang of this at this point. Getting a single term in the expansion. The coefficient of x squared in the expansion of 2 minus cx to the power of 5 is 720. Find the possible values of the constant c. So of course, you know, we might need to work backwards, do some problem solving using what we've done to find out what c is. So if I looked at that expansion, if I quickly just draw out Pascal's triangle, I'm looking for the 6th row, or the row with 5 as the second number, because that's my power. So 1, 4, 6, 4, 1, it's going to be this one, 5, 10, 10, 5, 1. Okay, so I'm looking at this row of Pascal's triangle, these are my coefficients, and I'm looking for the term with x squared in. So remember, I'll be having 2 to the power of 5 to start, 2 to the power of 4, 2 to the power of 2 to the power of 2, 2 to the power of 0, and the other term in my binomial expansion will always be the minus cx part, but raised to increasing powers this time. X to the power of 1 minus cx to the power of 2. Now I'm going to stop there because, you know, obviously I could fill it in, but I'm interested in the x squared term, which is going to be formed by the... oh blimey. It's going to be formed by this part of my expansion. So my coefficient is going to be 10, my power of 2 is going to be to the power of 3, and my power of minus cx is going to be squared, and that's going to give me the x squared term. None of the other terms are going to give me x squared because the powers of the minus cx part aren't going to be 2. Okay, so we know that 10 times 2 to the power of 3 times minus cx all squared equals 720, because that's what the coefficient is of x squared. If I just simplify this left hand side, I've got 10 times 8, which is 80, and minus cx squared gives me c squared x squared. Sorry, this should have an x squared in it. 720 is the coefficient of x squared. 720 x squared, and so I can just ignore the x squared parts and just focus on the 80c squared equals 720. Well, that means that c squared must equal 720 divided by 80. So 720 divided by 80 is 9. So c is going to be equal to positive or negative 3. So it's the square root of 9. Okay. So if you see any examples like this, just do the expansion, but obviously don't do the whole expansion. Try and just hone in on the part of the expansion that relates to your power of x for whatever coefficient you're looking at, and go from there. Okay, last part then. Let's look at this question. So maybe pause, well, definitely pause here and have a go at this question yourself. I'll talk through the answer after. You can always skip through a little bit and check you got the right answer. So find the first 3 terms in ascending powers of x. Ascending means increasing powers of x of the binomial expansion of 2 plus kx to the power of 7. Okay, so for part A, I need to quickly write out Pascal's triangle until I reach the line that I need for the power of 7. I'm not quite there yet, so I'm going to have to do this. I mean, coincidentally, we're going to find an even quicker way of doing this in future lessons, but It's important to build it up slowly. 6 plus 15 is 21. 35, 35, 21, 7, 1. Okay, so this is the row of Pascal's triangle that's going to give me the coefficients for my expansion. And I only want the first 3 terms. So I'm going to have descending powers of 2 and ascending. So descending means decreasing. So it's going to start with 2 to the power of 7. Then we're going to have 2 to the power of 6. Then we're going to have 2 to the power of 5. And because the question only asked me for the first 3 terms, I'm going to just do it for the first 3 terms. I'm not going to do everything. And then I'm going to do the ascending, the increasing powers of kx. So we're going to have kx to the power of 0, kx to the power of 1, and kx to the power of 2. And that would obviously continue, but I'm going to stop there because the question only asked me for the first 3. So the first term will be these 3 parts times together. Well, kx to the power of 0 is just 1. So I'm going to have 1 times 1 times 2 to the power of 7. 2 to the power of 7 is times 2 times 2, that's to the power of 5, 64, and then times 2, 128. So 128 is the first term, plus the second one will be 7 times 2 to the power of 6 times kx. So that will be, just write down under here what this was. So this was 1 times 2 to the power of 7 times 1. That's where it came from. The next term is going to be given by 7 times 2 to the power of 6 times kx. 2 to the power of 6 is 64 times 7 times kx. So we're going to have 448 kx. And the third term is then going to be 21 times 2 to the power of 5, which is 32, times k squared x squared. So 21 times 32 is, hopefully my calculator is correct, okay, this is what my calculator's given me, so I hope you get the same thing if you put those numbers into your calculator as well. That is part A done. Just needed the first 3 terms, so I'm going to stop there. Then it tells us, given that the coefficient of x squared is 6 times the coefficient of x, find the value of k. So the coefficient of x squared is this part over here. It's the whatever we're multiplying x squared by. It's going to be 672k squared. And that's equal to 6 times the coefficient of x, which is 448k. That's however many x's we have. So I can now form an equation and solve it and find out what k is. It's going to be a quadratic. You know they love hidden quadratics. Right, so 672k squared is equal to 6 times 448k. Let's just work out what that is. So 6 times 448 is 2,688. 88k, 672k squared. Okay, and we now want to make a quadratic equal to 0 and solve this thing. So we'd end up with 672k squared minus 2688k equals 0. Solve that however you like, with your calculator, whatever. I'm just going to quickly solve it now. Okay, so you should get, however you solve it, you should get k equals 4. Obviously k equals 0 is also a solution, but it wouldn't make any sense in the context. We're told that k is a constant, and it's obviously not equal to 0. Okay, so on to practice now. So in your binomial expansion section in OneNote, you've of course got our lesson instructions, and in the lesson instructions I've asked you to now go to the My Maths task I've set for you, just to check your basic understanding of what we've just covered. So there's a separate video on how to log into My Maths if you need it. And then it will be practicing from exercise 8A. If you finish all of that, try and do some of the investigations on Pascal's triangle, do a bit of colouring in. Can be quite fun, and there's loads of lovely patterns in Pascal's triangle. So I'd love to see any of your colouring if you get onto that bit. And hopefully see you later in the week. Any questions, let me know on Teams.